Okay, hello everyone. So this week we are going to study this paper, Pointillism, Accurate 3D bounding box estimation with multi-raters, published by Pointillism from University of California, San Diego, and published in SenSys 2020. So this paper is a very good paper, very good SenSys paper, and I actually learned a lot in terms of the methodology and writing style from this paper. Let's dive into the details. So the problems here are as follows. So existing sensors in automotive systems like cameras and lidars fail in adverse weather conditions, such as fog or dust, that barely affecting radius. And also, second one would be specular reflections of wireless signals cause poor performance of radar point clouds, which are sparse point clouds. And so what this paper proposed is as follows. So traditionally we have only a single radar. So there's a radar, there's a transmitter, and also the receiver also assigned here. So single radar is if the transmitter transmits the radar, and we can, and based on the surface, we will have different reflection. So just imagine like when some radio signals transmit through the air, and also it's like here at this point, it's approximately like a mirror. Just imagine there's a mirror here. Although it depends on the materials. But here we're just trying to illustrate the concept here. So if we have a single radar, what would be the problem? Well, so before that, we want to get a sense why we want to use radar. So we have radar. We transmit those radio signals. We receive those radio signals reflected on other surfaces, and then based on those received signals, we can actually infer some many things. One would be the detect whether there's an object. That's a pretty common case. So here, let's say if this radar transmits some signals and then reflect it on the surface and back to this region, then we can actually the sensor receives something here, and based on the that's details, and the high level thing is that we can detect something is here, right? And that's the key point. So that if this is typically incorporated in some cars, some autonomous car, for instance. And if there's something here, then we know if we detect some objects here, we can actually like avoid this object before actually crashing into this object, right? So if we have single radar and the other claim this is the traditional way, then it misses the reflective surface due to specular reflection. So what is specular reflection? Basically, you think here there's a mirror, and then when we transmit some signals here, there's a mirror here, and when this is a 90-degree, so it will then the signal will reflect it on the surface, and based on this line, and we'll have two same angles, and then the signal will be reflected to and traverse in this direction. So then if we have only one radar, and if it hits here, it's fine, we can receive something. But if it hits somewhere else, because here the surface of the surface it is like almost perpendicular to this traverse direction. So we can receive the single radar receive some signals from this reflection. However, if the signals are traverse in this direction and other directions, when these surfaces are not perpendicular to this direction, then those signals will be reflected into other directions. Then our sensor will not be able to receive those signals. So what we get is that there's not we can't get anything here, so we can't infer if there's anything here. So what the authors propose is multi-radar. By multi is actually that there's only two in this paper. So multi-radars, and when we have two distances here, we place two radars, and with some distance here is greater than 1.5 meters. Why this number? Then we can check it later. And then so what the authors propose is multi-radar setup with optimal separation, receives reflections back almost surely from the reflected surface. So basically, suppose here's a car, is this object we want to, here's the object that we want to detect. And if we have the setup with two radars and with the distance equal or greater than 1.2 meters, then we are able to detect we are able to receive the signals mostly at the borders of the cars. So here transmit some signal here, back here, transmit signals here, back here, and then we are able to has much better inference in terms of object detection, even for those signals reflected back to other directions, which will not be captured by this signal. It's fine because we have another one here, and we can capture. We can receive signals from this border. So here's the main the whole idea of this one, and the following is actually based on this one. And then let's look at this. Go back. Okay. So here, specular reflection. So here's some challenges in radar point clouds. So what we see is that there's some point clouds here. I mean, what are point clouds? Basically, the 3D points in an environment, and then well, basically that's it. And so basically here we have P and Q. Let's say here is the mirror, and we have some signals traverse in this direction, and then here is the normal, and the signal will be reflected and go into this direction, denoted in Q. Simultaneously, the angle of I and R are identical to each other. And the second challenge would be radar clutter and noise. What does that mean? So, like the noise is pretty common in sensors. Basically, there's some unwanted things in the signals. Common will be Kelson noise. And the other would be radar clutter, just like unwanted echo. So the best one would be we transmit the signal once and back here once. This is the best signal that we can, and the quality of the sound will be pretty good. So somehow, if the So here it's a very ideal case. We have only one car here. Suppose we have many cars around here, and if we have maybe some cars here, and if the signal goes in here and reflect back here, and it's not ideal because it just makes things complicated. So the sun character, especially in congested environment like cities, and there are different complicated sources in cities, and there will be, and we see lots of complicated reflections, basically. And then sparsity. Third one would be sparsity of the point clouds. So LiDAR would be very dense. The benefit of dense is basically in the environment, if there's nothing, you see very few point clouds from LiDAR. But if there's some objects, it's pretty dense, so it's very easy to find the salient part if we have dense point clouds. So here is another illustration, right? So here we have the vehicle, one count of scene with one target car. Target vehicle means that that there's something here using multiple radars. So red triangles, green dots are two different radars. So let's say we have two radars, and one of so that there's some vehicle here, and we can see those blue points by LiDARs, and so this triangle and in red, and also these dots in greens are radar signals, and we can see some if there's some radars here when we transmit something here, reflected back here, we receive the signals, and we take some. What we get is the raw data with those points here, and so the points in this area are pretty good because these are points that we want because we can because it align with the true vehicle here. So we want this one. So multiple path noise. Here's one example of clutter noise, and here's example of multipath noise. So multipath noise basically when there's some complicated refraction surfaces in this environment, and when we send some signals, it just reflected back and forth into somehow way in some way, and then we receive some signals here. And this is false positive. We don't want this one. This is the multipath noise. Okay, so and the effect of scene geometric, how geometry of the scene affects performance. So radars with the perfect resolution simulation. So to do that, they use a CAD model of a car along with its material properties, and then span the car in 360 degrees and 360-degree steps, and then they use single radar and two radars with varying separation distance. The purpose of this one is that, let's see, go to here. Scene orientation. So, wireless inside simulation. So here they do this experiment in simulation. Point clouds with single radar or smaller separation will lead to ambiguity in pose of the car, which gets eliminated by increasing radar separation. Orange and so basically, let me go back here. So here they have 1.5 meters. Why this number? Know that we have this variable distance between two radars, right? So the thing is that how what's a good number here? So I mean I can place it, I can put two radios just 1 meters far away or 2 meters far away. How do I know which one is good? So they try to find, to answer the question, they try that first. They try the single one. By single one it means that, so here the ground truth orientation, if this car has two different orientations, but for single one, what they receive is the same or pretty similar point clouds. So basically, when radar here and hits surface here back here, and somehow they only receive this thing. So the range is, if you look at this angle and this angle, the surface here are pretty similar. I think I hope to draw something. Yeah. So if we look at here and here, and even if the orientation are different for the cars, these surfaces are pretty similar. So what we got is a single here, and this point are pretty similar to this point. Okay. But if so, like if we have two radars, let's say the distance between them is 0.5 meters. And so so two different cars denotes the signals from two different radars. So here in, let's see, here in this direction we have here, but here we have some points here in orange, which indicates the longer side of the car. If then we have this point clouds here, which indicates the rear of the car, then we can actually infer this car is facing towards this direction. So here we are simultaneously, if 1, 2, 3, if we increase the separation of two radars, we see that we can see this long edge here, right? And more importantly, we can see this edge denser and denser when we increase the separation, this distance, which makes us more confident for inferring the car's orientation. Here's short. Oh, sorry. Let me go. Short to long. So similarly here, we can infer this long side. This is the short side, and we can infer the orientation here. And when we have 3 meters, then it's pretty confident that this car is in this direction. So this graph is trying to illustrate it, a very similar thing. For single radar, it's very ambiguous in terms of the car's orientation, only here or up there, which one is hard to infer. But if we increase the separation of two distances, we have much more confidence in inferring the vehicle's orientation. Okay, and then go to here. So here we have only like 5 examples. They sweep. They get this one. They scan the car in 360 degrees in 36 degree steps. And here's so they try here separation from average error. If the separation is 0.25 is very high, and we increase, and we see the elbow here 1.5, and it drops. Errors drops dramatically for the mounted, and that's why they pick this number here. And the other one is that it's because this one is actually the things that is also based on the statistics of the because in this context, because they're trying to detect vehicles, while a vehicle is how it commonly is has this 1.5 meters in length. So that's why they choose this number. And for single radars, it just is very high. So okay, and then so here's the in figure A is the regions of reflection of car and specularity versus resolution. So in the observed point cloud 0.3, so resolution basically how dense we want to send the signal, how dense we can receive these points. So 3 is missing due to specular reflection. I think this is vaccine just things a mirror reflection, while point A is formed from points 1 and 2 due to limits. And then so there's something like ghost cluster. So what ghost? So formation of ghost cluster due to multipath. So if the here is we have another surface, if we transmit another column signals here, reflect it here, and then reflect back here. So what we see here is actually that there could be something here because our radar transmits a line of sight direction, and although in the ground truth there's something here reflected back here, but what we see is that there could be something here. Similarly, for the other radar transmit reflection back here, what we see, what this can see is actually another points here. So these points are not actually in these it is in this position, the location. So that's why they call them ghost cluster. And this reflection in the environment is called multipath reflection. So these are some of the challenges when using radar. Space coherence with radar points potential. So how to use this data from multiple radars to encode information regarding noise. To do that, they use clustering the point clouds, the DB scan, and then enforcing space coherence by defining coarse potentials. So it's like noise is independent in each radar. Points belonging to the actual server's object appear at nearby location consistently. So they post these CP, which is cross potential. How to find the correspondence between the clusters across multiple radius. The confidence metric if the two clusters belong to the same object. The intuition is that the cross potential between two clusters is inversely proportional to distance between two clusters centroid. So here CI is I cluster centroid and tau. So we have our point clouds in J the radar, and R is the a distance between centroid Cij from the respective nearest cluster centroid in case radius point cloud. Cross potential point cloud CPVC. So this one we can filter the points below a certain potential threshold to create a cross potential point cloud. The effect of different threshold values on CPVC, the use signal to noise ratio of a point cloud, and the total number of actual points versus divided by the noise points. So to do that, they have some comparison of SNR improvement over base case without CPVC. So for multiple potential thresholds, higher thresholds will reject more noise with diminishing returns. So in this blue region shows the cases with very low noise in the base case, hence there's no improvement. Red region shows the cases when SNR decreases severely for a higher threshold. Therefore, let's select 0.5. And here's the top. So here's the original scene, and the top view operator point clouds with different CPVC threshold. So here's the original rate of point cloud. We have 1 and 2. So we have some noise here, and if we set CPVC threshold with 0.5, we can remove the noise here. If we select threshold as 0.7, we remove 2 maps, and such as these points are the points that we don't want to remove. And if we set the threshold to be 0.9, we actually remove lots of the point counts for vehicle 1, which is too conservative, and this is something we don't want. So so here's one illustration of why using 0.5 here. The challenges in 3D bounding process estimation. CPV is detection of number of dynamic objects. To estimate a 3D bounding process for objects from radar point clouds has the following challenges: segmentation, sparse point clouds from radar. And the second will be uncertainty in bounding bus parameters, dimensions, orientation, and central location. To do that, they propose RPNet. So basically, it takes in sparse radar points. RP means radar points. Radar point counts as input and output accurate 3D bounding process. So let's go to the details of the network design. It can handle multiple objects. So we have 5 different placements of the anchor box around the point. And there's a segmentation by feature extraction and pooling. Then we have bounding process confidence prediction, mapping from anchor bounding process representative features to the confidence value for each box. And we have refinement of box parameters. So estimate height, width, length, x, y, z, and orientation, responding to refinements of length, breadth, height, center coordinates, and orientation angle, respectively. To do that, they have the loss function. Basically, this is a binary prediction in the log form, and P is the predicted confidence value. So basically, this one is cross entropy, a binary cross entropy between the ground truth, yes and no. And then we have the refinement smooth L1 where R and R prime are ground truth and regressed refinement values and respectively for each parameters. And here's some illustration of the particular 3D bounding process using only one radar, along with ground truth in red. The 3D IOUs predictions are 0.5 to 0.1 for phase and 8 respectively. The radars can be used as a standalone sensor for object detection despite sparsity and low resolution. And then they compare the RPNet outperforms point CNN and clustering based for variables estimation. So RPMR performs better than the RPSR system. CVPC-based combination further improves performance. CVPP-based fusion performs significantly better in hard examples due to noise estimation and prior hidden direction using space-time coherence. MAP performance of RPNet on test dataset compared to the cluster baseline. And again, they also have the performance comparison of different sensors in the presence of adverse conditions. So that plot shows the depth estimation performance of radar and LiDAR for an object directly in front of the sensor in the presence of fog. The right figure shows the camera image for the experiment. So here's some takeaways. Use radar, and we can have which can perform in low light conditions. And we have mounting radar with optimal distance specular to solve the specular reflection issues, and we have cross potential to reduce noise from multi-radars, and we have RPNet to learn representations instead of handcrafted features. Okay, thank you. And good.